So we're going to do another exploration of friction that's going to be part kind of discussion questions and part some experimentation. And so we are slowing down to take a deeper look at friction. So you probably already have some intuition about friction. For example, you know that it plays a role in causing objects to slow down and stop. And you probably know that it generates heat. Sometimes there's not enough friction for us to notice the heat. And also it will cause a loss of useful energy. And so I'm going to look at our conceptual model first of all. And we're going to kind of consider some wire brushes, consider a model, and then think about a tractor moving a concrete block and thinking about what does that look like at the surface level. Why is it hard for a tractor to move a concrete block like on ground as opposed to trying to move it on the ice? And then we're going to do demonstration. So, okay, we're going to start out with a kind of a mini quiz. And so we've got a tractor trying to pull a very heavy block of concrete across a rough concrete floor, but it's unable to move it. So the tractor wheels are just sitting there spinning and the block is not going anywhere. So I want you to draw a force diagram or free body diagram of just the block of concrete, showing an arrow for each of the forces acting on the concrete block. So you're doing, like I said, a free body diagram of the forces acting on the concrete block. And then on your free body diagram, be sure to label each force with a name for the force. Okay, so the first thing that we want to do is think about what is the direction of the resistive force exerted on the block. So we've got the tractor pulling it one way, and we've got resistive force also pulling on it. So which letter shows what direction the resistive force is going? So it should be F. We know that the tractor is pulling forward, and so therefore, let's see if we can do this. So we've got a tension force by the tractor pulling it forwards. I should set a good example. So we have Ft on the block by the tractor. And because it's not moving and we want our forces to be balanced, we know that there has to be a resistive force going backwards. And this is what we're going to call friction. So we have the force of friction on the block, and this is by the floor. And it's actually pulling it at the surface that direction. I'm calling this a fake demonstration because unfortunately I don't have the materials that I need to do it. But I want you to imagine two wire brushes. So exactly like normal brushes, except instead of having soft bendy material, the bristles are made out of wire. So they're very stiff. And so you want to imagine the situation where I have clamped one brush down and I've got another brush on top of it, and I've pushed them together so that the bristles are overlapping. And I'm going to try to pull this one horizontally. So I want you to indicate the direction that the top bristles will bend while I'm trying to pull. And then indicate the direction that the bottom bristles will bend while I'm trying to pull them apart. And again, I'm pulling the top one to the right, and the bottom one is clamped down. Okay, so now that we've thought about the direction that the bristles are going, I want you to indicate the direction of the force on the top bristles. And it's the bottom bristles that are exerting the force. So what direction is the force on the top bristles by the bottom bristles? And then what is the direction of the force on the bottom bristles that's being exerted by the top bristles? So I think in both of these, the top bristles are going to bend this way. So this is the direction of the bend. And so this is also the direction of the force. So this is the force. It's actually normal force, in case you're wondering, on the top bristles by the bottom bristles. And then as they're moving, or whether or not it moves, the bottom bristles are going to bend this way. And so that means that the direction on the bottom bristles by the top bristles is that way. So we're going to equate this to friction. And so we're going to think about, that's like our model, anchor model for friction. And so we're going to introduce something called the bumps model. So someone's trying to drag a block across a rough floor, and we want to know what would a magnified view of the surfaces look like. And they're not pulling hard enough to move the block. So I want you to discuss with your group mates what would a magnified view of the surfaces look like. Okay, so here is one artist conception. So we've got the floor has bumps on it, and the block has bumps on it. Notice apparently only on one side. So we want to know what is the direction of the friction force on the bottom surface of the top block. And so I'm just going to take this. So what is the direction of the friction force on this surface when we're trying to drag the block horizontally? And then what is the direction of the friction force on the floor? So what's the direction of the friction force on the floor? All right, I'm not going to answer it quite yet. So we're going to look, or we want to know which force is larger, the force of the block pushing sideward on the floor, or the force of the, sorry for the typo, thought I'd gotten them all, floor pushing sideward on the block. So we know that we're going to equate this to the bristles. And so we know for the bristles, when we look at the, let's go back to yellow, we know that there is a force on the kind of top, so we'll say on the block by the floor that is pushing this way. And then on the bottom, we've got a force on the floor by the block. So when we were looking at the bristles, we decided that the top bristles would go this way, indicating force this way, and the bottom bristles would bend this way, indicating force this way. And the forces, we're going to say, have to be equal. Okay, so we know that the force on the bottom by the floor is going to be equal to the force on the floor by the bottom. And all we need to do is look at the letters, and we see that they have reversed. And when we reverse the letters, hopefully you remember, that means that is a Newton's third law pair, which means they have to be equal to each other. And so if I'm thinking about a schema, I've got the block and I've got the floor, and one of the interactions is friction. The other one, I'll just draw it in to be complete. We know there's normal, and I'm ignoring the earth right now. We're not doing a complete schema. all we're doing is pointing out that this interaction right here where I've reversed the letters, it's the same interaction. We're just looking at the two different objects. So in this one, we're looking at the forces on the block. And for this side, we're looking at the forces on the floor. But again, it's the same interaction. Okay? And that's what in Newton's third law of pair, same interaction. We're just looking at one object or the other object that's involved in the interaction. Okay, so let's take a little bit, let's kind of bridge our two examples, the wire brush and then the bumps model, and that we're going to look at individual bumps. So consider a magnified view of two flexible bumps trying to pass each other but stuck in this bent position. And so this is, we can think of, this is our box and this is our floor. And the surfaces are rough when we have a magnified view. And as a matter of fact, we can think of them not just as bumps, but actually like these little bristles, okay? And so when they try to pass each other, the bristles kind of bend. They're very stiff, and so they don't bend too well, exactly like my wire brush. And so we want to know how do the sizes of what are the directions of the opposing forces? Well, like before, we know that this direction, we can just look at the direction of the bend. This is the force on the box by the floor is pushing to the left if our kind of force applied is this direction. And then we've got on the bottom, again, we can just look at the direction that the this little bristle is bending. We've got the force on the floor by the box. So those are the directions. And then what about the sizes of them? Well, we just look at the letters and we know that we've got these two. Same letters, opposite direction. This is a Newton's third law of pair. And so these are equal to each other, just opposite directions. So that's how friction works. So let's do application. So we want to consider if the tractor is now moving at a slow, steady speed. So we got the concrete block moving, and now it's moving at a slow, steady speed. So what happens to the friction forces when an object is sliding across a surface? How does this compare to the static case when there is a force on the object but it does not move? So does the bumps model still work? I think it does. There's no reason that the bumps go away. If that's really what's happening on the surface, the bumps aren't going to go away just because they're moving. And then how are the forces different when the box is moving? We know that the forces decrease, but we are still going to have the force on the block by the floor is still going to be equal to the force on the floor by the block. But we do know that the kinetic values are less than the static values. We want to think about why. Okay, here's my idea. When they are moving, we know that they're already bent like this. So this is when they're moving. And so I think that some of the energy, they're already bent. And so it's like I'm smoothing the surface out. And so it's perhaps this is why the sliding friction is smaller. So they're already bent when they're moving because they're like bending as they're moving past each other. And so that might be one reason why kinetic friction is less than static friction, is I don't have to add energy to actually get the bristles or the bumps to bend. Okay, so I want you guys to do some exploration. So we have these friction sleds, and they have different things on the bottom, like cork and rubber and Teflon. And then what you're going to do is stack them so that the kind of surfaces, the bottoms are in contact with each other. Okay, so this would be like cork on the top one and cork on the bottom one. And then you want to put a mass in here, and you are going to connect the friction, the spring scales. So you want to slowly pull the friction sleds with the spring scales. Notice, do the hook, not the barrel. But you don't want to do it so hard that the friction sleds move. And you may need to just hold the bottom friction sled. But the important thing, read the scales at the same time as you're trying to get them to move. It has to be the same time or you're going to get wrong data. Okay. All right. What do you find? If you did it correctly, you should find that the forces are identical, give or take a little bit because the spring scales are not perfect. And if they're not identical, you did it wrong. All right, so that's the static case. Let's try the kinetic case. So exact same setup, mass in the sled. And again, we're going to have like cork and cork facing each other. So on the bottom sled, the open end will be down. And you want to slowly pull the friction sleds with the spring scale so the sleds are moving relative to each other. Don't hold the bottom sled. You're going to have to do this quickly because the sleds are not very big. But the big thing is that while they're moving, I want you to read the scales at the same time. They don't need to be moving very fast, but they should be sliding past each other. Read at the same time. What'd you get? All right, again, you should have gotten the same number, give or take a little bit, just because we are not dealing with perfect systems. Okay, so we're going to go back and relate this. Consider if the tractor is now moving at a slow, steady speed. So we want to know, how does the friction force of the ground on the concrete block compare with the friction force of the concrete block on the ground? Ground on concrete versus concrete on the ground. Okay, so they should be equal. That's what you should have found with your spring scales. And the question is why? And the answer is because, again, we just look, same letters, all we're doing is reversing. This is a Newton's third law pair. We are looking at the same interaction. We're just looking at it on either the ground as the object or the concrete block as the object. Okay, last thing that we're going to do is you're going to try to hold a block against the wall just by pushing only horizontally. Okay, not up, but just only horizontally. And I want you to draw an FBD. Okay, or free body diagram. And so the question is, can you push horizontally and hold the book up? Draw the free body diagram. Which way does the friction force go? Okay, it should be H. So this is what your free body diagram should look like. We know that the force of gravity, weight, on the book by the earth has to go straight down. We know that we are pushing, so this is a normal force on the book by our hand. We are pushing it to the right. And we know that the wall is pushing back. So there's a normal force on the book by the wall. And because the book is not moving, we know that we have to have a balancing force. So this is going to be the force of friction on the book by the wall. So if we were doing a schema for the book, we would have hand, wall, earth. That would be weight. This would be normal. That's wall. This would be normal, and then we would also have a friction force. Some of you might be wondering, is there a friction force between the book and the hand? Absolutely, but usually we do not draw it. So, Okay, so how comfortable do you feel with identifying the direction of the friction force? Think about the bumps in your situation. What direction are the bumps or bristles going to go? And then how comfortable are you with the idea that friction forces are caused by surface roughness, and thinking about like bumps or bristles being bent is what is causing friction?